So for those of you who just saw the last talk in the plenary session, this really builds on some of that work and has a somewhat different conclusion than what Susan Dickerson-Lang was just showing, and that is that the gaps in the forest matter, but it depends on elevation, and therefore your forest management needs to take that into consideration. So I'm not really going to be talking too much about forest management, but at the end I'll describe the implications. So just getting started, in the seasonal snow zone, where we have a lot of snow and less rain, maybe just a small fraction of the winter precipitation falls as rain, so we're really in the snow zone. That snow acts as a subsidy, a moisture subsidy for the forest ecosystem, in the sense that the forest allows that snow to persist, and it uses that snow well into the warm, dry season when we don't have precipitation. But what about the zone that's lower than that in elevation, where we do have a much higher proportion of rain, that so-called rain-snow transition zone? And we're wondering, what is the role of snow in that rain-snow transition zone? And what happens as now that rain-snow transition zone is expanding and moving upwards in elevation along our elevation transect in our mountain watersheds? So just to tell you a little bit about how we think about snow in this region, it's really temperature sensitive. We call this the maritime snow climate. And the snow that falls is falling at temperatures really close to the melting point, to 0 degrees Celsius. I always work in metric, so I apologize in advance if you have to sort of translate that in your head. So it's always really close to that 0 degree Celsius temperature, and it's also existing even if it does fall as snow rather than rain, it's really close to the melting point. So our snowpacks are really sensitive to differences in temperature. And as you know, temperature changes with elevation. So as you go upwards, it's getting colder. So that's why we have this transition from the rain zone to the rain-snow transition zone up to the snow zone. So one of the questions that we have is then, how do forests interact with that snow, and how does the structure of the forest affect these patterns of accumulation and melt? So here's the broader study region of my research group, which is the Columbia River Basin, and then within that, the Willamette Basin here, right here. And then today I'm going to be showing you some results from our Mackenzie River Basin, which is a wonderful field study site. It's representative of a lot of the watersheds that you see in the Western Cascades, both in terms of its forest management and the elevation range and the rain-snow transition zone. So here's a little cartoon showing, here's our mountain watershed, and you've got, trees at all different elevations. And actually at the lower and mid elevations, it's really dominated more by Douglas fir and western hemlock and some grand fir. And as you get into the middle elevations, you start to transition more. You see maybe a little bit of grand fir and subalpine fir, and at the highest elevations, you get more mountain hemlock and subalpine fir and grand fir and a bit of noble fir. So just again to this cartoon showing you the snow zone where the winter precipitation, not the annual precip, but the winter precipitation, you're really getting mostly snow. A little bit of rain event here and there, but you're really getting a lot of snow. In the rain-snow transition zone, that's a dotted line because it moves up and down depending on the year. And, it's a real mix. At the top end, it's a lot more snow, and at the bottom end, it's a lot more rain. And then below that, of course, you're really getting mostly rain and the occasional snow event. So, but you have these forests that go throughout these different zones. Here are our study sites. They're the dots that are indicated. I can't see them. Here they are. These guys here and these guys down here. Here's our high elevation site. So we have sites at the low and the mid and the high elevation parts of the snow zone. So going from the rain-snow transition zone all the way into that seasonal snow zone. And we also have paired these sites so that we have what we call a low density or an open site paired with a high density or forested site. And so here's an example from hemispheric photos of the difference between a high density and a low density site. So the higher density site might be like a 90% canopy closure, where the low density open site might be on the order of maybe 12% canopy closure. And at the low and mid forests, we have higher density, taller trees. At the highest forests, we have like more lodgepole pine and more subalpine fir and mountain hemlock. And at the lower sites, they're really dominated by Doug fir and western hemlock. So we also have this in our region, of course, this patchwork of clear cuts and thinning. We have a series of measurements that we go out and make. These are in situ measurements where we have sites in the open and the forested where we're continuously measuring the meteorologic and snow characteristics. And then my team goes out and measures on a monthly and semi-monthly, every 2 weeks in the ablation season. They measure all the snow characteristics along transects to get the spatial variability through the high and low density forests in these paired sites. And what we found is that the snow retention in these sites depends on, one, how much snow is accumulating at those sites in the wintertime and how fast it melts. Well, yeah, because you have the input, which is the snow, and then the sort of, I wouldn't say output, but maybe in a hydrologic sense, the output. So, and here's just sort of a picture of the high and low density sites. One of these low density sites here on the right is a former burn. So the snow retention, though, depends on the elevation. It turns out that, so here are sites. When I'm talking in the subsequent slides about the low and the mid sites, the low site is just at the kind of the top of the rain-snow transition zone. The mid site is at the bottom of the snow zone. So those are actually fairly warm in terms of snow. And then the higher site really is really dominated by snowfall. Here are these results that I want to point out. If you look at the high elevation site, you see the green bar, which is the forest, and the blue bar are about the same. And again, I can't see this, whatever. The green bar and the blue bar are about the same in the accumulation period. Okay, so you're going December, January, February, March. They're roughly equivalent at the highest elevation site. Once you get to the melting period, or what we call the ablation period, the forested site retains snow longer. It's shading it. You get loads and loads of snow there. And so much that the canopy actually can't hold that much snow, the whole fraction of snow that's falling. So at the high elevation site, snow lasts longer in the forest. That's in direct contrast to what's happening at the low and mid sites, where you never really accumulate all that much snow in the forest to start with because it's landing in the canopy and you get a fair amount of rain that's maybe melting it out of the canopy. So you don't really get that much snow on the ground at those low and mid sites compared to their lower density counterparts. So at the low to mid elevations, you see what Susan Dickerson was just showing in her talk just a minute ago, that you end up with loads more snow in the gaps at these low and mid sites. So what happens then? What's this transition then between more snow in the gaps versus more snow in the forest? So we would like to, we're continuing this research. This is something that we feel is really important for forest management because, as I said before, as the rain-snow transition zone continues to shift upwards, these high elevation sites are going to start behaving more like these mid-elevation sites, and you're going to see more snow being melted out of the forest. So here's just a little bit of our results. I'm not going to dwell on these too much. It's just at the low and mid-elevation sites we have fairly high canopy interception. The proportion of snow in the gaps relative to that in the forest, that's how we're measuring canopy interception, the snow on the ground. We have much higher canopy closure at those sites, so the structure's a little different from the high elevation sites. So that we have to take in consideration as well. Also, we're getting less snowfall and more rainfall at those low and mid-elevation sites. That's that SWED, a snow water equivalent to precipitation. And I want to show two graphs that are a little complicated, but I hope you'll get them. The height of the bar above the horizontal line is positive energy. That's energy going into the snow and warming it. And those lines below the bar is energy that's leaving the snowpack. But what I really want to point out at this low elevation site is that in the open area, this is the open site, that low density site, that the red bar, that's the solar energy. That's pretty high relative to all of the other energy components. So sunlight is a big component of the energy balance here. And you can see that blue line there, that continuous blue line is showing you the accumulation of snow, the snow water equivalent. If you melted all that snow, how much liquid water would you get? That's the snow water equivalent in centimeters. And you can see it's accumulating and then it's melting. And so it's really a combination of all these energy factors, but sunlight is an important component in these open sites. And that's in contrast to the forested site at this low elevation site. So our so-called accumulation period, if you look on the left there, that blue line, you know, you accumulate some snow. Actually, our peak accumulation happened in late December at this site. Then we had some melt events and then some snow events. And then, but the point is that these sites, you can lose your snowpack and then regain it and then lose it again. And so at these lower elevation sites, the thermal energy, because the air is warm and the trees are warm, the trees are actually radiating heat. And Jessica Lundquist has shown this in some of her really interesting work, that at these warmer sites, the trees actually warm up the snow to the extent that you can have a melt event as a result of that long wave radiation contribution. And we see that with these yellow bars. See, the yellow bars are, at these melt events, the yellow bars are pretty high. And that's saying, hey, long wave radiation is responsible for the decline in snowpack. So it's so the forest energy balance is different in the open areas. The energy balance is different in the forest than it is in the open areas. And here's an example of what that looks like on the ground. Around the trees, it's all melted out. And then in the gaps, you have more snow accumulating and less of that snow being affected, being melted by the long wave radiation from the trees. So we need to include these effects in our models. Here's some model pictures, results that we had in our Mackenzie River Basin, where we did include some of these effects, but we need to, I think, do a better job of characterizing the forest structure. And this is sort of how we are characterizing, a couple ways of characterizing the forest structure using ground-based LiDAR, really high-resolution 3D. But poor man's LiDAR is, we can use the NAIP imagery, the NAIP, National Agriculture Inventory Program imagery, with some software that we've worked with to create forest information that you can include in your models. So in summary, forest structure matters, trees matter. We need to know about the canopy interception. We need to know about the solar and the thermal energy, that long wave energy. Temperature matters, which is the same as elevation in our part of the world. We need to know if it's rain versus snow. And forest gaps are important for snow retention, but it varies depending on the elevation. The effect of the forest depends on this proportion of rain versus snow and the canopy interception and the long wave. So food for thought. In a warming world where you have increasing temperatures, decreasing snow, and a change in this rain-snow transition zone, how is that going to affect that moisture subsidy for the forests? And if you're planting now for 20 years from now, or for a 50-year harvest or ecosystem maintenance, you need to think about that idea of the shift of the rain-snow transition zone, the difference of snow retention in gaps versus the forest, and how that's going to affect that so-called moisture subsidy for your forest ecosystem. Thank you very much.